Hello. In the videos prior to this one, we have learnt various techniques for calculating partition functions exactly. In this video, we now need to come to a sad realization. For many Hamiltonians of interest, it is impossible to solve for the partition function exactly. This is particularly true of systems of interacting particles. When we come up against such problems, we are thus forced to calculate partition functions, average energies, and equations of states for these types of systems using approximation techniques. There are various techniques that we can use to calculate the approximate microscopic properties if we are given a microscopic Hamiltonian. The most common ones that are applied in research involve the use of computers and brute force simulations, and we will study these techniques in due course. In this video, however, we are going to consider an approximation technique that involves approximating the Hamiltonian. The technique we are going to use is called the mean field approximation. And it is also widely used. In fact, in research, this technique is often used in combination with computer simulation. You thus use a mean field approximation to simplify the Hamiltonian. Even when you do this, however, you still arrive at an expression for the partition function that cannot be solved analytically, and that must therefore still be solved by brute force simulation. To be clear, we're not doing anything as complicated as that in this video. We are going to use the mean field approximation to arrive at an approximate Hamiltonian that we can use to study the Ising model. It will then be possible to insert this approximate Hamiltonian into the expression for the partition function and to solve for the partition function for this approximate Ising model exactly. To explain the mean field approximation, I like to think in terms of the way that we have thought about the various model systems that we have studied thus far. If you remember, in my previous videos, I have classified various model Hamiltonians using a matrix something like this. We've seen the various components of this matrix classify model systems according to whether the particles sit on a lattice, like the atoms in a solid, or whether the particles are free to move about, like the atoms in a gas. We've then seen that we can introduce a second classification by considering whether or not we include the interactions between the particles in our model. In general, we have seen that including the interactions brings us more grief in terms of making the mathematics more complicated. We are thus going to use mean field theory in this video to avoid all this complicated mathematics. What we are going to do is introduce an approximation that allows us to treat a system of interacting particles, so a system that is in this part of our matrix, using the mathematics that we've introduced for a non-interacting system. In other words, although we are looking at a system in this quadrant of our matrix, we are going to use an approximation that will allow us to solve for the partition function in the manner that we have used in previous videos to solve for models that lie in this quadrant of our matrix. This is good as it will make the mathematics far more straightforward. Without further ado then, let's apply this method and use it to study the closed one-dimensional Ising model. Remember that in the closed one-dimensional Ising model, we have a collection of spins arranged on a ring as shown here. Each of these spins can be in one of two states, either spin up or spin down. The Hamiltonian for this system has a term that describes the interactions between these spins and the applied magnetic field H, and a problematic term that describes the interactions between spins. The problematic term ensures that each spin interacts with its two nearest neighbours on the ring, and makes it energetically more favourable to have the same spin value on neighbouring spin sites. Remember also that we have to introduce a boundary condition on the summation, as shown here, in order to introduce the circular geometry of the lattice in our equations. The interaction term is obviously the problematic term, and it is this term that we would like to get rid of using the mean field approximation. The way that this approximation works is that we will calculate the average spin in the system. In other words, we will add together all the spins in the system as shown here in the diagram. We will then calculate the energy due to the interactions of a single spin by calculating the interaction between this average spin and the explicit spin variable on each site. Notice that in calculating this average, we will include the original spin, and that as such, when we use the mean field approximation, we are incorporating a spurious self-interaction term. In short, any given spin interacts with itself to a certain degree. This all makes more sense when we write the approximated Hamiltonian. When we use the mean field approximation, the approximated Hamiltonian is given by the expression shown here. Each spin variable still interacts with the magnetic field H in the same way. Now, however, rather than incorporating the interaction with the two adjacent spin variables explicitly, we incorporate these two interactions as interactions with the mean field of the spins, at the S in angle brackets, as shown here. Let's now turn to the calculation of the partition function. As we are considering the Ising model, the sum over microstates is the sum over the n spin variables, as it always is. The mean field Hamiltonian is then the expression that we just arrived at. When these two terms are inserted into our expression for the partition function, we arrive at the following. Notice that, as always, I have used the function z to convert the sum from 0 to 1 to a sum over the two possible spin values, -1 and +1. Now look at this expression we have just arrived at. As always, we could rewrite the exponential of the sum here as a product of exponential. Further notice that each of the terms in this product would only depend on one of the spin variables, so we can rewrite the sum of a product as a product of sums, much as we did for the lattice gas model. In fact, from here on out, the derivation is almost completely identical to the derivation we performed for the lattice gas. The final result for the approximate partition function is thus just the partition function we arrived at for the lattice gas, but with h replaced by h plus 2js, as shown here. The only remaining problem comes in the determination of the average S value here. This quantity is just an ensemble average, however. In fact, we can calculate it by taking the derivative of the logarithm of the partition function with respect to beta h, and by then dividing the expression that we arrive at by the number of particles. The final expression that we arrive at for the average spin is thus given here. The result that we have just derived is the key expression when applying the mean field approximation to the Ising model. To consolidate this material, you will find exercises here that you can work through in order to better understand the derivations we have performed in this video. Then, once you are comfortable with these derivations, you can work through some further exercises which examine this expression and what it tells us about the phase transition this sort of approximated system can undergo. With that in mind, I will thank you for your attention and wish you good luck with the exercises.